Welcome back. We're going to do some examples about forces. So let's talk about 1D, change in force, change in acceleration type problems. Okay. The first example is a box sitting on a table, and it has some external force F. Okay, we'll call F1. So this is kind of our starting point. We'll keep going back to this. So this center of mass is accelerated because there's an external force acting on it of F. Okay. If I double the force, then it means 2F, right? Well, what would happen to my acceleration? Well, if you look at the formula, net force is equal to mass times acceleration. If the force goes up, then the acceleration goes up. They're directly proportional. And so my original acceleration will now be twice the acceleration. If I double the mass, so now I've got two boxes set on top of each other. Well, really it should only be one center of mass. And so if I double the mass, then I've got and if you rearrange this a little bit, so the net force is divided by the mass equals acceleration. So if the mass goes up, then the acceleration will go down. So if I double the mass, the acceleration is going to be halved. And so if you look at Newton's second law, where the net force is equal to the mass times acceleration, this relationship is very usable to answer some quick questions about what would be predicted in terms of motion when you change various things. Now you can change more than one thing at the same time. So what happens if I doubled the force and doubled the mass? Well, then the acceleration would end up being the same, because if this went up and this went up by the same amount, then the acceleration would go up by the same amount. Okay, so it'd be 2 times. Alright, let's do another example. This is 2 dimensions. So let's take our box, and it's sitting on a table. I'm pushing the box with some force. There's force of friction opposite of the direction of motion. The table is pushing up on it, and the force of gravity is pulling it down. So just a standard 2-dimensional piece here. You call this the book on a table example. You'll see this scenario a lot. It's a good starting point. We want to put this in terms of acceleration. Okay, so we have the formula: the net force is equal to mass times acceleration. And then we also have this idea of the net force being equal to all of the forces in a particular dimension. Okay, and then we would bring those back together with the net force is equal to okay. We're going to focus on this piece right here. and just kind of talk about what's happening in the y dimension and what's happening in the x dimension independently of each other. There's only a few situations that I can recall that will actually go back to the complete net force, the total balance in 2 dimensions. Usually we can leave those in what's going to happen in the y, what's going to happen in the x. Okay, so the way you set this up, I want to know acceleration. Okay, so acceleration is happening in the x dimension. I'll show you what's going on in the y later, but for right now, let's talk about the acceleration. So what is acceleration of this box? Okay, I'm going to start with this form right here. The net force is equal mass times acceleration, but I can't apply the mass times acceleration until I know what's going on in the x dimension. So it's actually the net forces in the x dimension, and so that brings me down to the second equation. So the net forces equal all of the forces in that dimension added up. And so because our traditional coordinate system here, everything up and to the right is positive, and so my f of a is going to be positive and my f of f is going to be negative. Typically this goes into the direction of motion, so positive being forward. Alright, and so my net force in the x dimension is going to be equal to the applied force minus the force of friction. Now this is under some acceleration, so I can substitute ma into here. And when I divide over, I can talk about acceleration in terms of the net forces divided by the mass, just like we were previously, but now I've got some actual numbers that I could plug into there. And so this would be the acceleration in the x dimension, and it would be able to answer this question once I plugged in some numbers. Alright, so this is an unbalanced force because the net forces are not equal to 0. If the net forces are equal to 0, that means that this term right here is equal to 0. The only way that you could get that, you can't have an object with 0 mass, is if you had 0 acceleration. So what happens if I have a net force of 0 or 0 acceleration? So let's look at the y dimension. Okay, the y dimension, same process. The y dimension is net force in the y is equal to force normal because it's up minus force gravity because it's down. I'm going to substitute in my ma. It's not accelerating because it's not sinking to the center of the earth and it's not floating away, so that up must equal down. That means there's no acceleration here. So this term hits 0. So, mathematically speaking, the up is equal to the down. So force of gravity is equal to the normal force. This is a balanced force, or we'll say it's at equilibrium. I think there's 2 L's. Okay, so balanced force, equilibrium, where the net force is equal to 0. Okay, so you've got 2 kind of sides here. So if you want to know what acceleration is, you take the sum of all the forces in that dimension and you set it equal to ma, and then you plug in your information for ma. If there is no acceleration, where it's balanced, and it's pretty obvious if it's balanced because it's not accelerating. Now, it's not to say that it's not moving, it's just not accelerating. You could be in an elevator at a constant rate going from the bottom floor to the 32nd floor, and you could have a net force of 0, because the elevator is exactly balancing out all of the stuff being pulled down. So the weight of the elevator, the person in it, all that stuff. And so this could very well be moving, have some velocity, or it could be at rest. We don't know. It's just that it's not accelerating. So that's a careful distinction in there. All right. So this is kind of your introduction to forces. We've talked about Newton's second law. We've talked about what are forces, the two different kinds of forces, how to draw a force vector diagram or free body diagram. We've looked at the net force equation in 2 dimensions. We've looked at Newton's second law. We've looked at the angles, how to deal with the force vector angles. Balanced, unbalanced forces. We've looked at the relationship between acceleration, mass, and force. And you should be good to start working on some problems and start solving this stuff. So be careful of how you solve them. Make sure you're lining up your equal sign. Make sure you're starting with your net forces in the independent dimension that you're working in, and then substituting in Newton's second law, and then understanding what that means in terms of like balance, unbalanced, and that sort of stuff. Okay, thank you.